So let us wait for a few more minutes. Let others to join and then we will start. Is that okay with you, sir?
Yes, yes, yes. How many have joined actually?
3 only, sir.
3. Hmm. Someone will display my slides, no?
Yes, yes, yes.
Okay.
We'll take care of that. Yes.
Yeah. Okay.
Participants are joining slowly, so let us start with the overview of the workshop.
How
We'll
if
take
more
time.
than 10, 12 people have joined, you can begin.
See,
How
seven,
many are you expecting to join?
at least 30 will join.
30 you have admitted, and actually only 5 have joined.
No, no, total registered is 45
Mm-hmm.
and now joined is 8.
Okay. Once it crosses 10 or 12, you can begin.
Okay, sir. Okay.
Yeah. Nisha, we can start now.
Yes, sir. Yes.
Yeah.
So good morning, everyone. Unfortunately, my laptop camera is not working, so I'm not able to on it. So I just welcome you all for our one-day user training program on MTA. I also want to extend my gratitude to each of you for taking the time to join us today. Your presence here reflects your commitment to learning and growth, and I have no doubt that together we will make this workshop an enriching experience. Now, let me just give you a brief overview of what we have planned for today. Our workshop is divided into lectures and practical and practical session, and each session will be interactive and engaging with opportunities for question, discussion, and hands-on activities. So, starting with the introduction will in the introduction we will explore MTA key concepts, followed by the demonstration where we will learn the uses of the MTA and MTA SPAC with some test input data sets to reinforce learning and the practical use of the MTA. We will engage you in the hands-on case studies. This activity will allow you to gain hands-on experience with MTA SPAC and MTA, and in turn may be useful for your research project work or for the development of the MTA itself. We have set apart a question answer and the feedback session. We encourage you to ask questions, seek clarification, and share your insights throughout the day. We have also set aside time for a dedicated question answer session and welcome your feedback at the end of the workshop to help us improve further sessions. Lastly, as we will be near to the end of our time together, we will recap the key takeaways from the workshop and discuss the next step. Whether it's applying what you have learned in your professional life, continue your learning journey, and staying connected with the fellow participants. So let me just quickly browse you through the MSCC application support page, which we have created to continue with this activity and the uses of these softwares. So this is the MSCC application support page. I hope you have subscribed to the my mailing list, which we have sent the link in our earlier emails. So this is a support page where you will get all the information about the software which are developed under materials and science, materials and computational chemistry project of NSM. So we have also created this discussion forums. I request all of you to join these discussion forums. So be connected in the future and help each other to grow in materials and computational chemistry domain. And we have this announcement where we will regularly make the announcement of our upcoming events. We have this mailing list where we will announce our whatever activity is going on under these projects. So I request you to subscribe to this mailing list to keep updated and connected with each other. We also have this ticketing section. If you have any issues using these softwares or you have any suggestion, you can raise and ticket and contact us. And we have this wiki page created where you will find the short description about the project. And we have the link provided for the detailed description. So let me just quickly introduce our key speaker for today's workshop, Professor Shridhar R. Gadre, sir. Professor Shridhar R. Gadre, sir, is a INSA senior scientist at Department of Scientific Computing, Modeling and Simulation at Savitribai Phule Pune University. Sir has done his MSc in Physical Chemistry at University of Pune in 1972 and PhD in Chemistry at IIT Kanpur under the guidance of Professor P.T. Narasimhan in 1979. Sir had several important positions. He was a postdoctoral research in USA during 1978 to 80. He was lecturer, reader, and professor at University of Pune from March 1980 to May 2010. He was professor at IIT Kanpur during July 2010 till July 2016, and he had taught several courses in physical chemistry. Sir is specialized in theoretical and computational quantum chemistry. He is authored 256 research articles published mostly in core journals such as Journal of Chemistry Physics, Journal of Physical Chemistry, and so on. Sir has several awards and honors. Sir has elected as a fellow of the Indian Academy of Science, Bangalore in 1991, and a fellow of Indian National Science Academy, New Delhi in 1996. Sir has also awarded the Shanti Swarup Bhatnagar Prize in Chemical Sciences in 1993, J.C. Bose National Fellowship by DST, New Delhi in 2007. A mini conference on molecular electrostatic potential was organized at Virgin University, Bruxelles to honor his work in this area in 2014. Sir has visited several university and research institutes in India and in several countries such as the USA, Germany, France, Hungary, Spain, Malaysia, Singapore, Australia, New Zealand, Japan, China, Taiwan, South Korea, South Africa, Brazil, etc. for his research stays and seminar and invited lectures. Sir has also edited the volumes of so many important journals, like especially issue of journal chemistry sciences on theoretical model for molecular structure, properties, and dynamics. Indian Academy of Science, Bangalore, in 1994, edited two special issues of the Journal of Computational Chemistry on molecular electron densities and electrostatic potential 2003 and 2018. Sir has organized several conferences and workshops on theoretical and computational chemistry. Sir is also book authored of electrostatics of atoms and molecules by S.R. Gadre and R.N. Chista, an educational monograph published by Universities Press, Hyderabad 2000. So I just thank you, sir, for sir is kind enough to accept our invitation, and thank you, sir, for taking the time out from your busy schedule for this workshop. In closing, I want to emphasize that the workshop is not just about acquiring knowledge. It's about building community, bringing like-minded people together, further development and transformation in the area of materials and computational chemistry. I hope that you will leave here today feeling inspired, energized, and equipped with the valuable insights and skills that you can apply in your studies and professional endeavors. Once again, thank you for being here. Let's make this workshop an enriching experience together. So over to you, sir.
Yeah. Yeah, thank you, Nisha, for that very elaborate introduction.
Thank you. Yes, sir.
And
Yeah.
am I audible to all? Participants can react by sending a message, or am I audible to all?
Yes, sir. Yes, sir. You are audible.
Okay.
Yes, sir. Yes, sir.
But I see only 21 participants. I don't know how. Anyway, very good. Now, can I have my slides, Nisha? Hello.
Yes, sir. We are sharing. Just a minute.
Yeah. I would like someone to display the slides. So, yeah, you can make it larger screen. Yeah, good, good. Most of the participants are PhD students or some are faculty also.
Some are faculty also, sir.
Okay, very good. So, warm welcome to you all on this. I don't know how it is in your place, but in Pune, we have had unprecedented rains in the last 2 days. So it's all flooded around, and I'm very happily sitting in my home and giving this talk. Very good morning to all of you. So my talk is about something that we developed over last 25 or more years, and I will give you a glimpse of this. And the carry on message to take home after this lecture is, if you sleep during the remaining part of the lecture, I would like you to carry this message with you, that ab initio calculations on large molecules and clusters are very difficult because they scale, as I will show you in the lecture. But something that we have developed, algorithm and code, we call it molecular tailoring approach. It will enable you to do ab initio studies on large systems, which you cannot do very easily using black box codes. I think some of you may be familiar with the black box codes in quantum chemistry. Most popular one is called Gaussian. And then there are many other softwares which have come up. Uh, One is GAMES, other is Orca, another one is Psi4. There is something called NTChem, NWChem, and so on. The most popular is Gaussian. And you will find that if you try to do ab initio calculation on large systems, it will fail. You know, you will run out of resources, disk, memory, and so on, and you will be thrown out of the software if your systems are very large. So this was the idea in developing. So those of you who want to treat accurately large systems and cannot use black box codes for the reasons I explained, come and use our molecular. We are invited to use our molecular tailoring approach. That's the reason for giving this talk in this workshop. Okay, and I'll be telling this like a story. Feel free to send me questions by chat. Or later, we will also have it verbally, actually, by communicating through audio or video, whichever way. So, again, that's the message. And let us begin. Go to next slide. Hello. Yeah. So at the outset, let me thank my two institutions. On the left, some of you might have visited these institutes. So it's Phule, Savitribai Phule, Pune University, where I worked for 30 years. And on the right is the IIT Kanpur famous fountain, where I spent about 13 years of my life. And then those of you who are interested, I'll give you two very, very important references if you want to use the code. There is a review on weakly bound molecular clusters, which we wrote in Chemical Reviews in 2014. And also another article which I wrote with Nityanand, whom you will hear very soon, in accounts of chemical research which gives you a review of our approach, MTA approach. Okay, let us go to next slide. Okay, so the gist of what we do is the following. And this is a recap of basic quantum chemical or a little beyond those methods. On the left, top left, you will see a large protein, and then you see a property of that displayed. So calculations on such systems are very difficult by using ab initio methods. You use semi-empirical methods, starting from UKL theory, EHT. Please go back. Please go back. Go back. Yeah, I'll tell you when to go next. Okay. Till then, I will spend typically 3 to 4 minutes on each slide. And if you have participants have any problem, please send me a message using chat box. Then you have semi-empirical methods. Then on the next part of the spectrum come the Hartree-Fock method, which is a basis of all the correlated ab initio methods. And then come more harder methods, more accurate, but limitations are there. So you will see Moeller-Plesset 2, MP2, and then you go further, do the configuration interaction, and then there are coupled cluster methods, which I'm sure you have heard of, if not already done. Okay. So what are the main bottlenecks in this? One is they scale very steeply. Doing even a Hartree-Fock calculation on more than 500 or 1000 atoms is very difficult even today. That is because they scale non-linearly. For instance, Hartree-Fock theory scales as the fourth power of the basis functions in principle. And the methods such as MP2 and what you see, coupled cluster and CI, they scale even more steeply. Just to give you a feel of that scaling, see the figure histograms on the bottom of left-hand side. What I have shown is a first graph in whatever violet, purple, whatever color, is the time required for water clusters, single point energy of at Hartree-Fock level. You can see that for water 16, it is very fast. Now, if you go to water 25, it becomes already somewhat difficult. These calculations were done with earlier days in Gaussian 09. Now, if you use a more accurate method like MP2 with an augmented, I hope you are familiar with these basis sets that I am talking about. Very elaborate basis set with diffuse and diffuse functions and added to it and polarization functions and so on. The Moeller-Plesset second order perturbation theory calculations, you cannot very easily do water 25, as you can see figure in the middle. It is very, very difficult to do. It takes huge amount of time. And then if you use a more sophisticated, elaborate, resource demanding method like CCSDT, you can see that you can barely go beyond water 8. Direct water cluster calculations, I will show you later the state of the art. It requires huge memory disk and very large amount of computer time. So here we come to the right. These are the main bottlenecks that I told you. So it's very difficult to do large systems, ab initio calculations. And that's where shortcuts come in. So people have developed these fragmentation based methods. The idea is you take a large molecule, cut it into pieces, and then devise ways to put that information together and derive the property of the large molecule by doing so. Such methods are called fragmentation methods. I'll give you a brief bird's eye view of these methods in the next 2 or 3 slides, and then we will go into our own method, which is called molecular tailoring approach. So remember why it is called this way, because a tailor will work the same way that our method works, or we work similar to a tailor. A tailor will take a large piece of cloth, cut it into parts, overlap them a little bit, and then stitch them where they overlap. Okay, that's the way it goes. Please send me by, if you have something burning issue or any query, send me by chat. I'll be happy to answer. Okay, or I'll include it in my presentation as I go on. Is this clear? I want you to take a break for a second. We take a molecule, cut it into parts, and then I'll tell you how we put it together. That's the way the fragmentation methods work. I hope it is clear. If it's unclear, please send me, or even if it's clear, send me a chat message. I would like you to stop for a minute here, think and tell me. Now, of course, how the fragmentation is done, we'll go to that in the next few slides. So the basic idea is, which I want you to absorb here, is you can do large molecule calculations by cutting the molecule. Cutting is not physical. Cutting is only in computer, virtual, and then stitching it all together to get the property of the large molecule. All right, so let us go to slide number 4. Yeah, Shivanandan, the answer to your question is coming in few minutes. Okay. Yeah, so the journey was very long actually. The first paper that was published on this topic in a very crude way, very bad computing facilities during my PhD days. It was by Ralph Christopherson in Proceedings of National Academy of Sciences. He was already talking about uh, doing polypeptide. Shivanandan's question was that. So somebody tried that in 1972. But I should say that those calculations were very, very, very simple. You used only one Gaussian function per electron pair in the molecule, which is today's world, it is unacceptably small number of bases. Then my friend Waitao Yang wrote a nice paper in PhysRevLet. He calls it divide and conquer method. That happened. Yeah. Neetu, don't anticipate questions. I'm coming to that. So your questions will come, answers to your questions will come as we go on. Our method, I'm very happy to say we were early pioneers in this. 1994, that's where we coined the term molecular tailoring approach. And we calculated electrostatic properties of molecules using that. I will show you a little bit later what we did. Next slide. Slide number 5. Yeah. And then many people joined. There is a group in Japan called Kitaura and Federo. They developed what they call fragment molecular orbital method, FMO. Then Collins from Australia. Then came Nakai from Japan. Basically similar, but in details they differ. Each method differs. Zhang came up in 2003. So all these people have developed their own methods, basically based on fragmentation. Okay. FMO has become very popular. It is a keyword in games and Gaussian. And I would like you people to start using our indigenous MTA, which has several advantages, as I will show you in the next few slides. Next slide. So here is a central theme of what we do, MTA and the people who developed. So basically, as I said, you take a molecule as is shown on the left top. It was a silicon, a kind of zeolite-like structure. And then there are hydrocarbons on which we tried, okay, early systems. And the name was given by my ex-student, a friend now, Ajay Limaye, on the left below first picture. Uh, we used to do fragments, write the structure of a molecule in pencil, then you chop it off and then you generate the coordinates of the fragments, do ab initio calculations, and then calculate the properties. Then the second man from the right, below, from the left, I'm sorry, Babu, he developed a very good method of how to cut a molecule. So for this purpose, uh, you draw the tree structure of the chemical graph of a molecule. He wrote the whole program. And I should point out that everything that we have done is indigenous. At the back end, we use a black box code, but all the developments that we have done are our own developments. Then the third person is Ganesh, who developed a very good software to do automatic fragmentation. And that code is available. It is called Meta Studio. Somebody asks you how large can you do it? So the answer to that is there is a code available for doing reasonable fragments of a large molecule. Anuja came in and developed, added a little bit to this. Then Sachin, whom you see on the next, in the next picture, we developed a code on molecular clusters, and I'll give you a glimpse of that. And then on the right, you see Nityanand, who is a very ingenious person who developed further refinements, such as calculating the gradients, calculating the Hessian matrix, and then geometry optimization was developed by a bit earlier, but he took it further. And then uh, rightmost person is our bright computer science person called Subodh, whom you will hear. So you will hear straight from the horse's mouth, as people say. Nityanand and Subodh will tell you more details of all these developments. I'm going to give you an overview. Okay. So is that clear? One is you can do fragments of a molecule manually. I'll tell you how little bit. You can calculate properties. Then there is an automatic fragmentation code available. Very beautiful code developed by Ganesh. It is available on GitHub. So you can put Meta Studio and Ganesh, you can download or you can use the code. Then we can, given a molecular geometry, you can calculate the energy, the gradients, the Hessian. You can carry out geometry optimization. You can do IR and Raman spectra. And these are the capabilities of our code. My phone is ringing, but I want you to stop for a minute and tell me whether you understand the capabilities of our code. You can do this, whatever you see on the top right part of this slide. Today, you can do all this. How some of this we will see on the next few slides. I hope you understand the reasonable capabilities of what you can do. And you can do this for systems which you cannot do normally with a black box code, as I will show you. So let us go to next slide. Hello. Yeah, okay. So let me take you to the first work that we did long ago in 1994. And then we developed this algorithm further. Two properties that I will discuss today is molecular electrostatic potential. See, molecules contain nuclei and electrons, and they generate an electrostatic potential around them. And of course, there is a charge cloud, electron density. So we developed this software in the very first paper in 94, and then we took it further in 2003 and 2004, as you can see in the references. So you take a large parent molecule or cluster, then you cut it into overlap fragments, carry out calculations. They can be either Hartree-Fock or they can be MP2 or whatever. Then you generate the density matrix of the fragments and then patch them together to synthesize from the fragment DM. I put together cleverly and I synthesize the density matrix of the parent system and use this density matrix to compute the electronic properties EMD, MED, and MESP. Okay. Things are very fast. You don't have to do the calculation on the whole molecule, is the bottom line. Next slide. And next slide will show you, yeah, that's a cover page. It's an advertisement of our paper long back. Myself, Shirsat, and Ajay Limaye, whom you saw. Next slide. Yeah. So before I go into details of that, let me give you our master equation. The master equation is how do you put together the property of a molecule? I will take an example of energy. So suppose, and this is actually justification of fragmentation methods was given by a paper by Walter Kohn. He calls it nearsightedness principle. It was published in PRL Physical Review Letters in 1996. So while fragmenting, as some of you are curious, we can, of course, the fragments of a molecule cannot be very large because if they are large, we lose the purpose of doing fragmentation. So they need to be of some optimal size. And I'm showing how do we put together the property, the energy of fragments. So suppose F1 and F2 are two fragments that you see in the figure. And the common part is F1 intersection F2. You may remember the Venn diagram in set theory, in class 10, something similar to that. So what is the master equation for energy? The energy of the whole molecule is sum of the energies of the fragments minus the sum of the energies of overlap fragments plus the energies of sum of energies of ternary overlaps and so on. So you keep on doing this. And this in set theory, it is called inclusion exclusion principle, applicable to the number of elements in a set. That is normally discussed in an undergraduate course on set theory. Now the important thing is we imported that equation for properties. And if you apply it to a molecule, what you see is number of atoms is preserved and number of chemical bonds are also preserved when you do fragmentation. Okay. And you can work out in similar expressions for all the properties. I can calculate energy gradients. I can calculate Hessian matrix elements. I can calculate the density matrix I hope many of you know what is a density matrix. Pij, it's the symbol. Okay, so that is the sole, very important part of our development, based on very simple principle called inclusion exclusion principle. Okay, I hope I would like you to soak it in the next few seconds and then we will go on. When we do fragmentation, we will check whether the number of atoms are preserved. Every atom in the main molecule is included at least in one fragment. Every bond in the parent molecule is included at least in one fragment. If it's included in two, then it should be there in the overlap fragment. Okay. So that's the basic idea. Let us go to the next slide. Hello. Okay. Now some of you were curious. So some early example I will show you. So this is a molecule, organic molecule. So what you do is I cut it into two parts, F1 and F2. Parent molecule is shown on top. I have chopped off one part on the right, and then I have chopped off one part on the left, and I have generated F1 and F2. Okay. And there are common elements in F1 and F2. So that is the F1 intersection F2. Now, of course, when I cut a CC bond during fragmentation, our chemistry should be correct, or physics should be correct. So I saturate it with dummy hydrogen atoms. In a molecular cluster, I don't require dummy atoms. So if you have a water cluster, I don't cut hydrogens of a given water. I keep water molecule intact. So in clusters, I don't add dummy atoms. In molecules, I have to saturate and add to take care of chemistry, the valency and so on. Is that basic idea clear? And I think our codes are available. You will practice. So some kind of rules of thumb. Don't normally cut double bonds. We can cut single bonds or weak bonds. And if you cut a covalent single bond like CC or NC or CN, or then you saturate it with a dummy atom. Normally, you don't cut planar rings. But actually, we played with it later and we treated the polycyclic aromatics also using our method. But that is too detailed for our workshop. Then there are rules. Send me by chat. That will be better. I'll read it and I'll include it in my presentation. If you have a doubt or anything needs to be clear, send me a message by chat and I'll be happy to address it. Normally, we don't cut multiple bonds. Normally, we don't cut planar rings. Non-planar rings, we cut properly. And all this wisdom is built into our Meta Studio. Okay. You may not realize how long we took to come up with such basic rules. It took 3 to 5 years. And yet I cannot claim that the rules are still very complete. They're pretty good. They work for most of the molecules, including polypeptides, proteins, and so on, as I will show you. So bottom line in you read, fragmentation is a pragmatic approach, but you have to take care of accuracy. You have to take care of efficiency. Okay. Because it shouldn't take too long. It shouldn't demand very heavy resources. And yet we should not lose accuracy in doing the calculations on large molecules. So all this is kind of addressed in our manual as well as automated fragmentation code. And today, my next people who bear the baton, you will hear them. They are young and very dynamic people, Nityanand and Subodh, much more young and dynamic than me. So you will hear more details of this from them. But at this point, is it clear that we do fragment molecules, normal molecules, normally organic, inorganic molecules, and then we have a way to put them together and generate the results. Okay, so that's the, I hope you will carry that message from here. Let us go to next slide. Please send me your query by, later we'll open with, you can ask on audio or video, but you are free to send me query now. Okay. So this is a cartoon picture. Not exactly very good in the sense that you have the input. Now you can see that the fragments overlap, very important. Fragments do overlap with each other. Now I have shown them separate. So 4 fragments here. And then everything is done by my wonderful people, Nityanand and Subodh. We have written Python codes to submit, make this job of those 4 fragments. It is submitted to something that runs at the background, as I have shown you on the right hand side. You submit it to games or Gaussian or any other package. Right now, what we will show you is using Gaussian at the backend. So fragment calculations are done by Gaussian currently or by games. Then you generate the energies and the gradients uh, if you are doing geometry optimization. And then comes the Python patcher. It will just put together the results using the, I have shown you the master expression. That is cardinality based expression, it is called. So you have the way to put together the property of the whole molecule. Okay, so that is the basic scheme of things. Very easy to use, as my friends will show you in the next 2 sessions. So we are a little bit close to halfway. So please send me your queries. I will take a break for half a minute for you to think. Of course, Shubhojit Das, you can send me by chat. Okay, so I would like you to carry this message with you for the next sessions. Very simple. You have a molecule, you fragment it into overlapping, large molecule into overlapping fragments, either manually or automatically. You do calculations, and can you see the beauty of this? All the fragment calculations can be done in parallel. For example, as I have shown you, the first fragment can run on one machine, one node. Second fragment can run on another node. Third fragment can run on. So like that, very, very trivial uh, parallelization. It was very lucky for me that CDAC was next door to my department of chemistry at university. And we had a very, very long arranging collaboration with SEDAC. They funded me well for a small team and access to hardware. And that's how we could develop all the details that I have shown on this slide. So inherently parallel, that is what the message you should carry. Next slide. Yes, next slide. Yes, I'll show you. I think some of you will be wondering. So here is one example. And this is a very simple illustration. Okay. The parent dipeptide is shown in the center. So that is the, don't worry about what it is. It is a dipeptide. Now I cut it into two parts. I try to keep the balance. Okay. Parent molecule has 16 into 232 atoms. I'm illustrating only with two fragments for this slide. First fragment has 19 atoms. The second fragment on the right has also 19 atoms. And NBF means number of basis functions. We use a very large basis. Suppose you want to do correlated calculation, you use augmented CCPBDZ basis of Dunning. And you can see that from 498 calculations, 498 basis functions in the parent molecule, I have 300 basis, 297 to be precise. So I have reduced the calculations. I can do 3 fragments and make it even smaller, no problem. So that is my very simple illustration, which was prepared by Nityanand and Subodh. The next illustration is on a little bit more involved system. Go to next slide. Yeah. Large, well, a schematic. Polypeptides are not straight like this, but I have taken a model system. So beta strand of alanine polypeptide with 159 atoms. Naturally, you will cut at some place CC bonds. So you will see how it is broken into roughly equitable, not exactly equal, but equitable fragments. So you make in such a system 5 fragments. Typically, how to judge whether a calculation is good enough? So for that, we have a parameter. How good is a fragmentation scheme? We call it R goodness, radial goodness parameter, which we define in a certain way. It is incorporated in MetaStudio also. And then we can do, for example, on these fragments in polypeptide, we have done IR and Raman spectra. Fragmentation becomes difficult for more involved structures, as I will show you. And for such very simple thing, manual fragmentation is easy. We just take a pencil and cut like what I have shown you. Okay. But life becomes very difficult if the structure is very complex, as I will show you on the next slide. Let us go to next slide. Yeah. Well, you cannot see it very clearly, but here is a fragmentation scheme for a water cluster, water 25. Now there is a person called Sotiris Xanthias who has been doing this work for many, many years. He is the world's best known person for water clusters. Yet, the structure that I'm showing, he cannot do that easily at CCSDT level. So we use automatic fragmentation code here, which is developed by Ganesh. You can give the required parameters, as Nityanand and Subodh will show you some examples today. Okay, so you can see how many fragments you need for such a system. This is a very simple scheme. So we restrict the size of the fragments. 14 water molecules is the largest fragment. 13 water molecule, no fragment of that. 12 water. This is generated by the automatic fragmentation, which takes care of the so-called goodness. It tells you how good the scheme will be in terms of interactions missed out. Okay. So these are what the automatic code generates. The fragments are shown in the highlighted. They are highlighted. Maybe you cannot see it, but so for a complicated system, the fragmentation is better done automatically, not manually. So two messages for last 6-7 slides. A, you can fragment all reasonable molecules in organic, inorganic chemistry. You can do it manually or you can do it automatically. And then you know that the results are going to, I will show you how good or sometime not so good are the results. Okay. So let us go to next slide. Okay, one question. Somebody was curious. So this work, I don't remember exactly. Around 2000, we did this work, or 2005 or something. It is called TRP cage protein. And we took the PDB file from the crystal data. The name is called 1L2Y, a typical name of a code of a protein. It has 20 amino acid residues. And they said it is the fastest folding protein that they have seen. So we were curious. Of course, those years doing Hartree-Fock geometry optimization of such things was also difficult. Now we can do much better. So there are 5 charge centers such as NH3 plus CO minus. You can fragment such systems very nicely, and it has an overall positive charge which is conserved because of our inclusion exclusion principle. Okay, so we did that, and that time we did a geometry optimization at Hartree-Fock and a single point MP2. So you can see the errors in Hartree-Fock, and this is a lesson to learn. Hartree-Fock, doing Hartree-Fock gives larger errors because Hartree-Fock energy expression, you will see it picks up energy contributions from somewhat far off atoms also. Whereas E2, the perturbative correction in MP2 is much short range. You can see the errors are very, very small. And you can see if I do S1, S2, S3 are with fragments becoming larger and larger, or at least different. And you can see that actual time taken for the whole molecule, single point energy calculation, 977 minutes that time. Fragment calculations took about less than 200, of the order of 200 or less minutes. So this was our early illustration for a protein. You can do it much better today with the technology that my colleagues will show you, and as we will see on the next slides. So let us go to next slide. Okay, then chemistry opened its doors. Once we had it ready after 2005, we took up studies of large systems. Okay, so one water cluster we took as an example, single point energy calculation. Unfortunately, at Hartree-Fock and B3 density functional theory, times were rather old. And then we also calculated Hessian matrix. Just to those who have forgotten Hessian matrix, These are the second order partial derivatives of energy with respect to the nuclear coordinates. Okay. So I calculate them. I do a full calculation. Once I do a full calculation, I can see the errors. So this is for benchmarking. Okay. And you can see how accurate the IR frequencies come. Okay. The errors. So for water cluster, it comes to about 3200 centimeter inverse. For beta carotene, some of the frequencies I am showing you. And the time taken for MTA frequency calculation, top line you can see 172 minutes. Whereas if you did actual calculation full, 1180 minutes. So you have a tremendous advantage in doing vibrational frequency and intensity calculations to calculate the vibrational IR spectrum. This was a study with Ganesh and Anuja, long back, published in JCP 16 years ago, just to see how accurate are the frequencies. Then came Nityanand later into this game. Let us go to next slide. Next slide, please. Yeah. Okay. Then Nityanand came into my life. And then we developed this. See, whatever you do, there will be an error in the calculation. The error can be sometimes large, sometimes small. Why the error comes? Because you are doing calculations on fragments and some interactions, maybe little long range, are not included in any fragment. For example, on the left I have a fragment, on the right I have a fragment. No way I can interact. They interact with each other. Okay. So we developed what we call as a grafting procedure to kind of mitigate that error, to address that error. So what we do here is we take the MP2 calculation, okay, from a smaller basis. We do a full calculation at the smaller basis. We do an MTA calculation at the smaller basis. That is the error. And we graft it on the larger basis. What I am showing you here is little more elaborate version, but there are two versions of grafting procedures. But those are details which some of you will learn later if you want to use the software. It is also automated. The code is automated, so you don't have to do grafting corrections manually. So what is the purpose of this? The purpose is to mitigate, to address the errors that arise due to missed interactions. We applied it to these water clusters, 20 or even 25. And that was a paper in Physical Chemistry Letters. You can see the authors are, one is Pradipta Bandyopadhyay from JNU and our group in Pune. Mind you, these are not very easy calculations, not very easy to do at MP2 level of theory. Okay, let us go to next slide. Okay, here, can we go beyond MP2? And then don't worry about that equation on top, very similar. So you do MTA calculation and then you correct pick the correction from MP2 level. But you can see what is remarkable is you can see the accuracy of numbers. If you did a full calculation, which was done by Xanthias, you can see the rightmost column, EFC is the full calculation result at CCSD coupled cluster, single doubles with perturbative triples. And then you do those calculations in a fraction of time Mind you, these calculations were done by Xanthias using hundreds of thousands of nodes, 100,000 nodes, very large number of nodes. And our calculations are done with one or two desktop machines, which are on the left. Okay. And middle one shows you the correction. After grafting correction, what are the numbers? So if you compare second column with the third column, you will see barely a difference which is more than 1 milli. It's not there. The numbers are accurate to 1 millihartry. That is about 0.6 kilocalories per mole, if you convert. So that is the best test case. I can show you water cluster with MTA and the grafting correction. It's amazing result, very, very amazing result. You can compare the column 2 with column 3. And these are done on very few single, your desktop machines. Okay, 32 GB RAM. Both advantages are there. You don't need huge RAM, you don't need huge disk drive, and you don't need many nodes. So here is something, as the saying goes, you have the cake and eat it too. You have the cake and eat it too. You can have accuracy, you can do with small hardware and our indigenous idea of fragmentation. Okay, so far, let me recap last 5 slides. We can do ab initio calculations at high level of theory on normal clusters, normal organic molecules with very, very good accuracy with minimal hardware. Okay, keep that with you. If you have anything, send me a message in chat so that I can address it in the next part of presentation. I'll wait for a minute here. Have some hot water. Yeah, maybe we go to next slide. Yeah, okay. So we called it that way. Gold standard. See, CCSDT at augmented CCPVDZ or TZ is a gold standard. I have put some table on top. If you did full calculation, extrapolating the scaling, it would require 32,000 minutes on a large cluster. And water 25 will require phenomenally large time to do full calculation, whereas with our MTA, with grafting, it is possible in 9,000 minutes. Very. And last slide, I have shown you how accurately they match. So we wrote a paper with, as I was mentioning, Xanthias is the world's expert on clusters. So we took up a joint study with him and published that in JFIS Chem Letters many years ago, 14 years ago. Okay, next slide. All right, then grafting correction. See, once you have the technology, you can correct everything. All the properties I can, because they are in error. The results will carry some error, not very large error, but there is a way to reduce the error. That is done by grafting. So we implemented with Nityanand, whom you will hear his brilliant talk after me, Subodh, and he will give presentations. So how do we calculate more accurate Hessian metrics and more accurate dipole derivatives. Same technique. I do it with fragments and I do the grafting correction. Okay. MP2 minus HF, I graft. And then I have shown you one conformer of water, the most stable water 16 conformer. And you can see the errors. The errors are listed there. Very, very, very tiny errors in energy. But the lesson of the what I presented is you can do. It's an art of the possible. Okay. If you have a very large system, don't worry. We can handle it. We can handle it with sufficient accuracy and sufficient efficiency. Let us go to next slide. Next few slides, I will show you demos of how accurate are these results. These are all basically, next few slides are taken from Nityanand and Subodh's works. So what are two figures I am showing you? Gray figure on the left is done with MTA and the red one is with full calculation. And what I am showing you is the intensity versus frequency of vibrational IR. You can see there are differences. Some gray peaks do not match the red peaks, which are the full result. But it works like a magic once I apply the grafting correction. So on the right hand side, I have used the grafting correction. We have used the grafting correction. And you can rarely see that these are two different curves. One is red, one is red and one is blue. Can you see? I hope some of you can see, but otherwise not very. So that's the wonder of error mitigation. Okay, error mitigation that happens on grafting. Now look at the amazing timings. Full calculation took 10,000 minutes. Including grafting, our MTA calculation took roughly 1/7 of the time or 1/6 of the time. 50 minutes, much less hardware. You don't need huge hardware. Okay. Because you do only calculations on the fragment. In grafting, you need calculation on the full system at a very low basis, much lower basis. So calculations are easy, hardware is smaller, and this is a Nityan will tell you more details. Okay. Next slide. Yeah, next slide. Okay. Well, you can say advertisement of Nityanand's work. So on the left, you will see water 25 and just MTA. And then you can see below the respective grafted figures. This is water 25. The region on the left top figure is OH stretch frequency 3100 to 4000. And earlier regions on the right. And on grafting, it works like a magic, as you can see. The two curves they match very, very well, barring a little something which you can see some difference here and there, but not much. So moral of the story, if you need a vibrational IR spectrum, theoretically predicted at ab initio level of theory, for large system, don't give up. Use MTA. It will give you accurate results without a significant loss of accuracy. Free to send chat message if you wish. Next slide. Okay, I'll go through quickly some latest works. I don't want to go into details, but one use of this is for dynamics people. Because all the dynamics calculations, sophisticated ones, require a potential energy surface. For example, I have shown you acetylacetone on the left. Now that proton tunnels between, it goes from oxygen on the left to the oxygen on the right. Huh? And same story on tropolone on the right below. So when the proton is hopping, proton is moved from that position to the next position, you need potential energy surface of several geometries. And there are people like Professor Joel Bowman, who works at Emory University. I'll tell you some story of our past student, Apurba Nandi, worked with him. And he said, why not use molecular tailoring approach for generating the potential energy surface of these systems? So we did. And we published at CCSDT, augmented AVTZ, augmented valence triple zeta basis. We reported the basis set. At this high basis set, we reported the CCSDT level potential energy surface. Very hard thing to do. Okay. See, and what is the beauty? The beauty is our method. We don't have world's best hardware. We have pretty good hardware with NSM now, but surely it's not the world's best. But it's the idea that we made it work. Next slide. I'll just go through very quickly some examples. Next slide, please. So this is geometry optimization in IR spectra of proteins, which we published. You will hear from Nityanand and Subodh, who are the authors of this paper published last year, JChemPhys, geometry optimization and IR spectra of proteins. As you can see, they work very well in general and for the systems, with grafting, without grafting, whatever. And people always asked us questions, what about solvent? So we can put a continuum solvation model. So we publish that with continuum solvation model also. Some of the results in pink, and gas phase results are in blue and pink, possibly blue and red, whatever. Okay. DFT. So you can use any basic method. You can use DFT, you can use MP2, Hartree-Fock, and for smaller systems, CCSDT. And one fun thing is these two people who are world's experts now, Nityanand and Subodh, will tell you in the next sessions little more details of everything. Next slide. Yeah, so these are details, don't worry. That proton hopping I was telling you in tropolone, okay. This is not the purpose to give you a lecture on how they fit the potential energy surface. They have a very elaborate method to fit the potential energy surface and do dynamics with that. Okay. So this was a paper in JAX with Joel Bowman and our group. Our job was to produce very accurate potential energy surface for the proton hopping in tropolone. Let us go to next slide. Let us go to next slide. Yeah. So we are open to this, and some of you who do biological or biochemical or whatever calculations, we can generate PES for peptides. What made our great Ramachandran very famous, the sci-fi plot, a great scientist from India who came up with this idea of Ramachandran plots. You can calculate now with more sophisticated methods. I can vary phi, psi, or I can vary many dihedral angles So we have taken two examples, alanine, alanine and alanine, proline. It will be a pleasure and fun to go further, but I do need collaboration with, some of you who are interested in such works on polypeptides. We can go. Even tetra pentapeptides, we can generate the PES, as you can see, with very good level of theory, at least MP2. Okay, so that is one avenue I can see of our work being used meaningfully for generating the potential energy surface. And I welcome uh, any suggestion from you in this regard. Let us go to next slide. Hello. Yeah. Okay. Now I switch the topic and tell you something that I have been doing with another of my student, Dr. Milind Deshmukh, and that is using the ideas such as MTA for doing something very good, which nobody has done before. Let me tell you what I mean by that. You know that there are hydrogen bonds, a term coined by Linus Pauling long back. And if you have a water dimer, the one on the top left water dimer, very simple to calculate the hydrogen bond energy. Or if you have an ammonia dimer, the middle picture, or a HF, hydrogen fluoride dimer, very simple to calculate. What is the strength of that single hydrogen bond? So what you do is you calculate the energy of A and B, that is AB, put together in optimized geometry, subtract the energy of A, free optimized A and free optimized B, and that is the bond energy. Typical number in water dimer, as all chemists should know, is about 5 kilocalories per mole. In ammonia, it is about 3. In hydrogen fluoride, little stronger, 4.5 kilocalories. So far this is very simple, but take an example that I have shown, and this fellow cartoon, it's wondering, the person is wondering how to calculate. If you have a water octamer, as I have shown you uh, below, how do you estimate the energy of there are many hydrogen bonds here. How do you estimate the energy of every hydrogen bond separately? So it all started with Milind Deshmukh's PhD thesis long back. Possibly, I don't remember the year, 2009, if I remember. Next slide. An idea here is very simple, as you will realize. So how do you estimate the energy of the hydrogen bond HB1 in prism that you see, parent water prism cluster, 6 water molecules? How do you estimate the energy of HB1? Answer, we discovered the answer, very simple. In one fragment, you remove water 2, which is forming HB1. In another fragment, you remove water 1, which is forming HB1. Okay? I hope you will carry the idea with you and you can apply it if you are interested in estimating individual weak bond energies. And then I use my MTA equation. Overlap fragment is shown there. So energy of parent molecule, energy of. Remember parent molecule as a hydrogen bond. The fragment is put together, I have done in such a way that the hydrogen bond is missing. So if I use my principle, I calculate the energy without hydrogen bond. And parent energy is with hydrogen bond. I take the difference and I can estimate all the hydrogen bond energies. So for example, if I do E of F1 plus E of F2 minus E of F3 and subtract from it the parent energy, I will get the bond energy. Remember, the bond energies are positive. Signs are positive for attractive interactions, the usual convention in chemistry. So it comes out to be 6.46. Okay. And if I did a calculation on the dimer just between W1 and W2, removing all other waters, that energy is 4.11. Okay. The remaining part, which is contributed by the network of hydrogen bonds around HB1, that is called cooperativity contribution. So we can calculate. We can calculate, and we did. And Milind has made his, very beautiful works, very detailed works. Uh, and I have been a part of some of them. He has done many other studies, but this is the basic idea. Use fragmentation method. HBEE, you will wonder what HBEE is, hydrogen bond energy estimation. Okay, so you can calculate in a given molecule, in a given cluster, and I will show you the examples. Next slide. So there is automated software. We published it in JCOM Chem. It's called HBEE code. It is available for using. If you want individual hydrogen bond energies in a molecule or a cluster, you can automate, or you can use automated code, or simply we can help you on that. But the code exists, and mind you, estimating individual hydrogen bond energies in a maze, very complicated maze of things, is not easy. You have to have a formalism. So we have the formalism, we have tested, we have written very recently, just yesterday, a perspective in Journal of Physical Chemistry, which Milind and I wrote, Milind and one of his students. It will appear. So if you are curious, please have a look. It is already online. Okay. How to estimate individual hydrogen bond energies in molecules or clusters. Okay, that is the subject. Next slide. Okay, and here is Milind, here is his student who did that work, and we have handled a variety of systems. Okay, so some of this Milind has done with Mini, some of the works. Some of the works I have been a co-author. So a polypeptide, our biochemistry friends may be interested how to determine individual hydrogen bond energies in polypeptides, because that does govern the way polypeptides or proteins fold. Okay. So that is a paper in long back, 2009. Then complicated hydrogen bond networks like calixarin, or these cage structures like porphyrin like, and then water clusters of various kinds. You can believe me, huh? I don't know whether you still believe me or not, that you can estimate individual hydrogen bond energies of all these molecules. Each hydrogen bond you can estimate very accurately and very efficiently. Okay, next slide. Okay, I think I have given you an overview of the method. Let me summarize. One is take home messages for you. One is large molecule ab initio calculations possible on limited hardware. Is there a great loss of accuracy? We have seen in no case we have a great loss of accuracy. We can do it on limited software. We can use more nodes because everything can be parallel in this. All fragment calculations are independent, and putting results together is very simple. We have handled energy gradients, second derivatives of energy, that is Hessian. We have developed an error correcting mechanism called grafting. So that's the capability. You can calculate vibrational IR and Raman spectra uh, after optimization of molecules at some level of theory, and you can do quite meaningful works. What I'm looking for, and that's the purpose in giving this overview talk, is there somebody interested in using our technology? Of course, somebody will say yes, but it takes long time to discuss and come up with a collaborative plan. Not very easy. You may think it is very easy to do, but it can be done. If there is some interest, real interest in enabling large molecule calculations, any of you has an idea or a system and is stuck for resources, we can do. So last 20, 30, 25 plus years, we have been at it. Everything is done indigenously. I have had collaborations with outside people, but not many from India, very few. But the technology is ready, codes are ready. And these days, NSM is doing wonders. It has established very good clusters in many, many places. So, thanks to NSM, some of you can access those clusters. How does it go further? Okay, one is MTA in conjunction. We have MTA very well tested code with Gaussian. We have somewhat tested code, reasonably tested with games also. And remember, games is a public domain package. So many of you can, all of you in principle can use with games. One outcome is, as I told you, you can calculate, you can do geometry optimization, use correlated level of theory. You can do Hessian, vibrational spectra. You can do on our cards, and I hope our Subodh and Nityanand will carry it further, a better geometry optimization based on Hessian. Because we have Hessian. Our method allows us to calculate the Hessian matrix. Then estimating strength of intramolecular hydrogen bonding and applying it to biological and other systems. That is on our agenda. We can use MTA for calculating. See, crystallographers these days can give beautiful plots of electron density and electrostatic potential calculated from spectra, experimentally observed, X-ray patterns. I want to bridge that gap. I want to calculate that for a solid using MTA and bridge the gap between the crystallographers and theoreticians. So that is on the cards. And next slide. Yeah, somebody is saying with a metal center. Yes, I think we have tried a few. I think we can try. It's a molecule with metal center, but not too many metals, but something like chlorophyll, or something with metal center, we can use our method. So last but not the least, let me say first, my first research project in my life in 1980 was from UGC. Then CSIR, I had some funds. DST funded me well through two projects and JC Bose Fellowship, as was mentioned in the introduction. CDAC has been a pillar of support, small support, not very large, but throughout from if I remember, 1990 till almost 2022. And then National Supercomputing Mission supported a project which supported some of the work that I showed. And I think it's wonderful time today, you know. There are very many NSM machines now throughout the country. There is ready software which permits you to, you know, not only mine, some others which my colleagues in IITs or other institutes have generated. So please come forward. Uh, Using a software is not very easy, meaningful. So that's where some interaction comes. And more details are needed, demonstrations are needed, and my friends Nityanand and Subodh will show you clearly. They will give you more details, some demos and some hands-on. Our software is quite easy to use, is the message I want to convey. It needs some training. Of course, it needs some training. And I hope some of you will come up. If we generate at least one or two common interest projects through this talk, which I gave for about 1 hour 10 minutes or a little more, hmm, 1 hour 20 minutes. The talk is worthwhile if we really come up with a nice, meaningful system to which you can apply our technology. So thank you very much for your attention. Some of you may have questions, and now we can ask in person, or still you can use the channel of chat. Okay. So we can take up a few questions by chat or by audio or whichever way. Yeah. Thank you very much. Thanks to the organizers again, Nisha and her colleagues. And CDAC team, there are 2 or 3 people who will also take part. They have been with us. They have developed a graphical user interface to our software. So they will also be there. I don't want to show next slides. Too many details are there. So thank you very much, one and all, and we take questions. Hello.
Huh? Sir, there are some questions in the chat. We are reading it out.
So the first question is, could we use this method for protein?
Yes, I showed you one slide, which we did long ago. Of course, some thinking has to be done. But we have, that work was done around 2000 something. I don't remember, 2005 or 6. So you can use our method. Two questions I have always encountered in polypeptides and proteins. How do you take care of the solvent medium? Okay, is one question. So we have the answer. You can do some kind of a continuum model, but putting water molecules in the places we do not know where they are. So protein in vacuum, no problem at all. Protein with continuum solvation model, yes, we can handle, we have done. And of course, such a thing doesn't go this way. I hope you are a domain expert in that. So you have a lot of knowledge of those. So some discussion, after some discussion, but on our side, no problem, barring what I said. Okay. So we could do protein of maybe of the order of a few hundred atoms or little larger also. A good parallel machine is available, little larger also. Is that a reasonable answer to your question? Yeah, her mic is off.
Yes,
Parimita.
there is another question from
Yep.
audience. Next question is, how big each fragment is there? A limit?
How big are the fragments?
Yes, each fragment.
Depends on
Is
the
there a
system,
limit?
you know. So the and level of theory. So the example of CCSDT that I showed you for tropolone, fragment size is 14, 15 atoms because you want very highly accurate numbers CCSDT level. But if you want on the other side, if you want a protein, very large protein, and you are happy with density functional theory, I think fragments could be maybe 50 or 100 atoms, 50 atoms, let us say. And you can easily circumvent the sizes of 1,000, 2,000. At DFT, no issue. Okay. So are you happy with density functionals for proteins? Hello. Paramita's mic is again.
Actually, sir, this question from audience, I am just reading this question. I am a
Okay.
coordinator of this
Okay.
workshop.
Okay. Okay. Okay.
So,
Okay. So the person who asked that question, uh, is he or she happy with, and which density functional would he or she like? That's the, but very much doable. Fragment sizes for proteins, a ballpark figure is 50 atoms, 50 atom fragments. Okay. Everybody is off.
now there is another question from audience. In your paper, like Journal of Molecular Structure, someone asked, the molecule like this in your study with a metal center can be studied?
Yes, I answered that also. I mean, not too many metal. See, metals have a very strange, metal clusters are very strange beasts, you know. So I have done some work on metal clusters themselves, but not too many works. But if you have, as I answered during the talk, if you have a molecule like chlorophyll or something with one or two, or even some molecule with 3, 4 metal centers coordinated to an organic framework like porphyrin or something, yes, we can study. I mean, I see no limitation.
Hi, sir. I'm Niru. I was the one who asked this question. I understood whatever you said. I have just something to ask. This is similar to a porphyrin ring, right? So I was thinking of a single molecule in the middle, like a hemoglobin or a myoglobin kind of a structure.
Hmm.
And when the oxygen introduction reaction happens on it, the metal
Hmm.
kind of moves, right? From the
Hmm.
planar to, I don't remember it is upward or downward, even though it is in
Hmm.
the inside the protein
Hmm.
structures. So
Hmm.
I just wanted to know, like if I look at a hemoglobin or myoglobin during the oxygen
Hmm.
reduction reaction,
Hmm.
I know that it have been done in theory previously, but I am not good at theory, so I don't know which system they have used. So,
Hmm.
will the same thing can be used with much more accuracy with this particular software?
We can do only one thing is see triplets and higher states, you will require some thinking.
Okay,
But otherwise I see no problem.
okay.
Okay. Triplet states, we need a slightly different treatment.
Mm-hmm.
So won't be straightforward application for closed shells that I presented, but it will be worth, if you have a simple example with a metal, a protein containing a metal, we will be happy. Chlorophyll would be very nice. Even hemoglobin we can try. Interaction of hemoglobin with something,
Mm-hmm.
but it won't be very straightforward, yet surely doable.
Okay. Yeah. Thank you, sir.
I think there
All
is no
other
more
people's
question.
are mics are off or minds are off. I don't know. Mm.
So I have one more thing to ask. May I? Nidu again. So you showed the IR spectrums, right?
Yes.
So for the Raman also, it's a similar calculation, or it's a different thing. Like we have to, if we take the second derivative of the system, we get IR. But for Raman,
Last part of the question I didn't get.
okay, you
Yeah,
have
I
shown
showed you
how to
IR
get a
spectrum of
Raman
few
test.
systems. Yes.
Yeah, so you have shown using the software we can get the IR spectrum. But
Yes.
for getting the Raman spectrum, what have to be done?
Same thing. Same
Okay.
thing. Code is there,
Okay.
as you will see in the next sessions. I think
Okay.
Subodh and Nityanand will tell you mostly about spectra. We have a separate code called MTA spec, which they will explain, and it is in public domain.
Mhm.
And they will explain more details, but vibrational IR and vibrational Raman, to answer your question, both are possible.
Okay. Thank you very much, sir.
Okay. And also our CDAC team will be there, who will explain to you how to use our code using a graphical user interface, which they have developed with Subodh and Nityanand. Okay, I think that's all for the time being. Thank you very much. Thank you, Nisha.
Thank you so much, sir. Thank you for taking your time out and addressing our audience for this workshop and on the MTA. So we'll just, as per the schedule, we'll just take a quick break for lunch. We'll
I wish you had arranged lunch over the net also.
next time surely if they ask more questions.
Someday.
Yeah.
Okay. Thank you. Thank you very much.
We'll ask
And
them.
I can join the next session also, no, using the same link,
Yes, sir. Yes, sir.
because I want to see how my, not boys, they are all grown up people now. Subodh and Nityanand do in the next sessions. Yeah. So thank you very much.
And just a minute, sir. Just one request for all of you, like just if you can on your camera, we'll take a group photograph here. Please switch on your cameras, sisters.
Okay. Here is Shankar. Okay. Paramita Ghosh. Okay. That is our team. Okay. Nitu. Okay. You are from where, Nitu? Her mic
Hi,
is
sir.
mute.
I'm from Mysore, Pune.
Hmm?
Mysore, Pune.
Mysore, Pune.
Yeah.
Okay. Okay. Very good. You are neighbors. Okay. Okay. Thanks a lot. Huh? Nisha's
Yes,
picture
and
is not there. I don't know what
my
she's doing.
laptop, unfortunately, my laptop camera is not
Okay.
working today.
Okay.
Thank you so much, all. We will assemble back sharp at 2 p.m.
Yeah. Okay. Thank you. Thank you very much. Shankar, see you later. Shankar is muted. Okay. Bye. Bye bye. Thank you very much.
Bye. Thank you, sir.